Welcome to the pre-lab webinar on thin layer chromatography. We'll begin with a brief intro to chromatography. We'll discuss terms relevant to chromatography, discuss the construction of TLC plates, discuss the mechanics of TLC, discuss the general method that you'll use and concise that down to an overview. We'll discuss spotting in detail, we'll discuss development, discuss visualization, and discuss how to measure and calculate retention factor. Chromatography in the briefest sense is a separation method. It's more powerful than the standard separations that you've done in the lab so far that were based more on density than anything else, or based on reactive solvents and then using density afterward. The big difference here is the fact that it's more dynamic and that there's usually a fixed or stationary phase, which can also be called media or chromatography media. It depends on the type of chromatography you're using. If you're using a liquid chromatography and it's in a column, it's a media, usually either like a gel of some sort that is placed in the column or suspended. Usually you have to kind of suspend it before you put it in, but it just depends on the column. And then if it's gas chromatography, it's based off of the boiling point, which is a little bit different. So it just kind of depends. TLC plates use a media, but the media is fixed on a plate and is kind of, in a way, sort of solid. The other phase is the elution phase or the mobile phase. And so there's constantly some kind of a solvent or elutant that is going through the separation method. And the rate at which different species will interact in the solvent versus the matrix of the media material is what gives you the theoretical plates for the separation. Now, there's a big difference here in some regard to the theoretical plates you'll find in chromatography columns versus a fractional column, because you don't calculate the theoretical plates entirely the same way. It is true that the column length is still probably the most important factor, but you also have to look at things like your volume, bed volume, and sometimes the retention times for different compounds can be different, and so this can change your plates too because it's very experiment specific. And so no literature is really out there that will standardize chromatography columns unless it's used a whole lot and everybody does it exactly the same way, because these types of separations are very dependent on your experimental method and you have to use the same one in the same kind of setup in order for the numbers that you calculate to hold true. And that's true even of TLC plates. So most people measure these things internally in their labs and they kind of use that as a guide for their own separation work rather than publishing all of it. It's just not something that's necessarily useful to everyone. But that's the main difference. And we will not get into calculating any of these plates or really discussing them because, as I said, that's a very complicated subject and it's very situation dependent. All chromatography involves certain terms. Even in TLC plates, we have synonyms with these terms, and we follow patterns of procedure that meet with these terms. So it's important to kind of understand some of them. The first term is the injection phase, which is a phase in which the mixture to be separated is loaded on the column, then it's injected in some cases, but that's usually only with the gas chromatography that you inject it. So you don't normally inject things into the column. The term injection comes from the fact that most of the chromatography that is done nowadays is done with a pump. And so you usually have a feed line that goes from the pump into a container where there's a solution that's suspended the thing you want to purify, and then it can load that onto the column, or you can load it with a funnel, load it in, and then apply a gradient across the column with a pump with an elutant that's pumped through another feed line. And so that's how high pressure chromatography tends to work, and some low pressure systems that are in biochem labs are set up that way as well. And so that's kind of why we use the term injection. Another reason we use the term injection is because when you do gas chromatography, you take a syringe and you inject the sample. You'll also find that, like with the GCMS, even in an auto sampler, there's an injection method in that a syringe is inserted into the scintillation vial by a robot, and it absorbs some of that compound to be put through the chromatography column. So it is literally injected into the analysis unit. TLC is different in that we don't actually inject the plate with a syringe. We do use a capillary tube to place a spot of the material on the plate, and so that's where the term spotting comes from, is that we're putting a spot on the plate of the compound. But what we're actually doing is injecting the media with a sample so that we can undergo a separation. And in that regard, the term injection and spotting are synonymous, because that is injection for this chromatography method. We just won't refer to it that way. We'll call it spotting TLC plate. That's what everybody says. And we'll discuss a procedure later and show some demonstrations of how that's done more adequately. As far as the eluting phase is concerned that we mentioned, that phase is the progression of the solvent through the media that's going to aid the separation. And so that can be achieved normally by the pumps on those bigger systems, but in this case it's by the solvent moving up the plate. And so that is the eluting phase for a TLC plate. And of course, you know, to maintain elution, you have to have the right setup, and that's even critical in a TLC experiment. So you do have to do things that promote elution. In the older days of doing chromatography, everything was done by hand, and so it was all gravity work, and they still do gravity columns for some things. When you do a gravity column, you have to continually apply solvent through the column by hand, because or you have to have a pump hooked up to do that part, because you've got to continually supply solvent. You never let the column go dry. That's just not done, and it can actually cause the column to be disrupted by letting it run completely dry. You have to continually keep the media in suspension. And you can reuse columns if you set them up this way. As long as they're wet and they have enough solvent in them, you can use a column for several separations. And usually after about 5 cycles, you'll do a procedure to clean it. And you can reuse the media. So the media is somewhat expensive, especially in biochem labs. It can run, you know, enough for 2 columns is probably worth almost $600 in some cases. So it can be quite expensive, and that's why we tend to clean and reuse the media if possible, because it's a lot of trouble to set it up, and it is a somewhat large expense. As far as the eluent is concerned itself, that is the solvent that does the elution phase, and it acts as part of the mobile phase and promotes the mobile phase. The elute are the items dissolved in the eluent. So they're basically, it's like solutes and solvents, eluents and elutes. And elutes can be many things. Elutes can be proteins, elutes can be salts, elutes can be organic chemicals or inorganic chemicals, depending on if you're separating them that way. Usually they don't put inorganic or organometallic type compounds through chromatography, because they usually crash out of solution pretty easily and they can just be filtered. But there may be a case out there somewhere where they're using chromatography to purify something like that. So you never know. But I'm sure they don't want to do that because it's hasslesome. As far as the difference between a column and a TLC plate, it's pretty large. TLC is probably the simplest chromatography method out there. It consists mostly of, in the modern day, a pre-made plate that has a sort of silica or alumina powder that's sort of adhered to a plastic / aluminum composite back to the plate. So there's like a backing on the plate, and then that stuff's kind of cemented on there in a way. It's not really cemented, but it's dried on there and it's compressed, and so it's almost like it is cemented, like a plaster or something like that. And that's advantageous because you can cut those plates into various sizes. You don't have to have a glass slide custom made to fit the material, because before what you had to do is take a microscope slide and you smeared the material on the slide, then you spotted it, then you put another on top and you ran it, and then you would if you had to do any kind of special development technique, you would have to take that top slide off and work with that, or you'd have to run it without it and let it dry on there. It would be very different compared to the way that we're doing it now, which is a little more streamlined and easier to do. I've never seen this done the old-fashioned method. I'm not saying it's still that it may not be still in use, but I've never seen anybody use this now because we have the pre-made plates and they're not too expensive. They are more expensive than some things, but they're not as bad as the media that you would get for like column chromatography work. It's very different. And so these are some simple drawings that I've made. I know they're probably not the best drawings in the world, but they kind of give us a general idea of some concepts that we need to understand about mechanisms here. So with the TLC plate, what I've drawn here is we're looking at the TLC plate as if you were holding it in your hand, looking across it, with the thin part being what I'm looking at. So let's pretend that this is a 5 by 10 centimeter plate. My 5 by 10 centimeters will be the area on the top, and this less than half a millimeter space here is what we're looking at. And you can see that I've drawn in some of these purple lines here. And what this is meant to show you and represent is that there's a matrix here created by the molecular network of the silica. And so if we put this down into the solute and we have injected it or spotted it, as we would say with TLC plates, with our substance we want to carry through for separation, then the length at which that substance moves along the plate in the vertical direction inside the development chamber will be correlated to the series of reactions that occurs between the binding to, or the favorability of sticking into the material of the plate itself, and the interactions that occur between the silica and the molecule, or the solvent and the molecule, and whether or not the solvent shields the molecule from interactions with the plate. And so, depending on those parameters, different substances will move further lengths at the same course of time along the plate with the solvent front, is what they call that. So as the solvent moves up, they call that the solvent front. And you actually are able to see the solvent front move. It looks much like that wetting a paper towel, how you can see the water change the color a little bit as it darkens the material. And so you will notice the movement. And that's important that you are able to see the movement, because you have to note where the solvent front stops in order to measure retention factors on the plate. So the factors most important, which have not been discussed, are those solvent parameters and the parameters the molecule has for which you would choose solvent. So some of the most important are the polarity, which can include hydrogen bonding in this case because that's a special kind of interaction that relates to dipoles and to electrostatic effects. But also surface area is important because you'll remember from general chemistry that a lot of molecules, if they don't have polarity, they have a degree of London dispersion forces or van der Waals forces, as they are more favorably called for myself. And so the longer a chain is, the more van der Waals interactions you can have. In some ways, molecular mass is tied into this because there is a correlation between surface area and molecular mass for isomers of the same class. So for instance, let's say we were observing the difference between N-propane and N-octane. There's going to be larger surface area on N-octane compared to N-propane, and there's also going to be a larger molecular mass. So those two coincide. But that relationship is not always necessarily true. Sometimes you can have a heavier atom or a molecule attached to a surface that is quite small and spherical, like a methane molecule versus a tet chloride molecule. So it's, or as they say, carbon tetrachloride. Everybody used to call it tet chloride as a nickname, but carbon tetrachloride is what I'm talking about. So, that would be vastly different. Yes, the surface area might be just slightly greater because of the angstroms difference we're talking about with the different atoms involved, but it's also fairly compact. And so in that case, the molecular mass is greater and the other is smaller. And in those cases, since in that particular case, the polarity would be negated to some extent by the fact that there's so many different directional pulling by the vectors, then you would probably see less movement compared to if it was methane alone. I'm not saying that that does happen. I'm just giving you the idea that molecular mass is something that can become important in sort of varying to some extent the movement of a molecule. And those are some examples that just pop into my mind that are kind of easy to comprehend. But the bottom line here is that you don't have to do a lot of fancy measuring in order to kind of pick a solvent. You can look at the properties of the compound. So, what I would typically do is look at the structure of the compounds I want to separate. If I know some are more polar than others, I'm going to try to add a little bit of a polar solvent in my solvent choice for my iletant so that when I do the separation, I'm sure that there will be separation between more hydrocarbon-oriented molecules versus the polar ones. So it's kind of a qualitative approach. And of course, if something has more hydrogen bonding than not, then something that's capable of hydrogen bonding will probably be better at working with it. So those are just some ideas to keep in mind. Now, you can get a little more physical if you want to with the measurement, and you can do the dielectric constant. And there are studies that have been done on TLCs and dielectric constants and trying to determine a rubric of solvents to use based on dielectrics. A more practical way to go about that, though, is the iliotropic series, which is basically the same kind of idea that I just talked about, where you have solvents that you know are least polar and then solvents that are most polar. And these are the typical solvents that are picked when doing TLC most of the time. So you have petroleum ether, which is mostly a grouping of alkanes and various hydrocarbon type chemicals that don't have much polarity or hydrogen bonding. And then you go up towards cyclohexane, toluene, chloroform, acetone, ethanol, methanol. Methanol is considered the most polar. Other things that have been used include ethyl acetate. It can be anything as long as it's a solvent that favors the materials you're trying to separate. And it's all about finding the right balance. Now, usually you try to use one solvent and one solvent alone. If that's not giving you a good separation, then you have to mix solvents to some proportion. And a lot of people might think, well, if I had this situation where I didn't want my methanol to be as polar, I could just mix some petroleum ether with my methanol and it won't be as polar anymore. But that tends to not always be true. It's not as negating as you might think it is. It turns out that if you mix them 50-50, you actually will have a polarity that favors more towards the polar molecule than you will the nonpolar molecule. So we tend to be very sparing with the use of polar solvents in those cases, and usually you would use more parts of non-polar to polar in a case where you were worried about that kind of a need for separation. And there are cases like that. In the case that we have here, we have chosen the particular solvents we have for you, and you don't have to worry about picking the solvents. We know they'll work. So that's removed some of the hassle. There are some very important factors in doing a TLC and doing it correctly, and it is important that you focus on trying to meet these criteria as much as possible if you want your plate to turn out the first time and not have a lot of errors that are possible. And so we'll talk about what those are individually. The first is your sample concentration. When you do a TLC, it's important that the sample that you're measuring is concentrated. You don't want it to be extremely dilute. That's one of the first mistakes that people make in this process. And the easiest way to go about that is to use the minimal amount of TLC solvent possible. It is important to note that when you do a TLC, you use the same solvent to dissolve the compounds as you do the solvent you're using for your elutant. You usually don't mix different solvents together because that would introduce new compounds into the equation. So when you do that, it's important to make sure you minimize the amount of solvent that you're going to apply in this situation. And you also want to be cognizant of your material. It's important not to overuse material in some cases, because sometimes you're trying to do this for $1 million compound or some kind of expensive product that you've been making, and you want to recover it later. But you also don't want to waste much of it doing something like this where you could chance the fact that it might not come back out again. So to err on the side of caution, you usually use a small amount, but you keep in mind that you want the minimal amount of solvent possible to keep it concentrated. In the same way, sample size is an important factor. Much like with capillary tubes when we did melting points, we had to examine how much we were putting in those capillary tubes. And remember, the rule with the capillary tubes is we don't want more than 1 to 2 millimeters high of sample in the tube. In fact, as soon as we can see sample, we really have enough to do an analysis in most cases. The same kind of holds true for here. We don't want the diameter of the spot that we put on the TLC plate to be larger than 2 millimeters. And it can even be 1 millimeter in diameter, and that is considered sufficient. I will say that that rule is probably the hardest for people to meet, especially the first time that they're doing the experiment. Because most of you have never spotted a plate before, and I have not even done it in some time. I might not get this right every single time. It takes many, many tries and many, many plates of experience before you learn how to spot one and get just the right amount on the plate. So don't fret too much if you can't get that size limitation, but try your best to keep it as small as possible when you spot. Okay. We will and we will discuss a method you can use to kind of help you meet that size when we talk about how to make your capillary tubes for spotting. The other thing that's important is minimizing contaminant. So one important fact is you should never use an ink pen to write on a TLC plate, because remember, most inks are organic compounds that are in a solvent, and therefore, if you put them on a TLC plate, you'll actually inject the plate with compounds, and they will travel possibly in the solvent and separate. So that is not something that you need or want to do with the plate. That would be bad. You want to use a pencil. I would suggest using a regular wooden pencil with a nice big broad piece of lead rather than a sharp pointed one, or a mechanical pencil that has the smaller leads, because the problem with that is they're going to have a greater tendency to scratch the material on the plate. This is also why it's important that you only put a very, very small mark on the plate instead of going all the way across. And I'll show you an example of what I'm talking about on another slide that has the examples drawn out for you. The other factor, aside from using appropriate marking tools, is that you need to avoid touching the material on the top of the plate with your hands. You should either wear gloves, or you should hold the plate by the edges of the plate or the corners instead of holding it on the material. What happens when you hold the material is that you're going to introduce any contaminants on your hands onto the plate. The oils from your hands may contaminate the plate. They could become part of the experiment. They could also block passageways in the plate if there was enough of them, and that could cause errant results in your experiment. So you don't want that. The other important factor is maintaining a vapor pressure over the liquid. If you don't do this, what will happen is the solvent will favor evaporating as opposed to running through the plate. The kinetics favor whatever's the least resistant. And you have to imagine that these small spaces in the plates are fairly resistant to flow. So for that reason, you usually put them in a chamber that can close off. There are actually TLC development vessels that are made specifically for the plates. I have used Palm Wonderful jars in the past to do TLC, and those work great because they're made out of glass and they have a cap that goes on top. And so they work really well. Mason jars would be a good option. Beakers that can have a lid put on them. And not many beakers do have lids, but you can place a watch glass on top and you can block off the ridge from which the pouring spout on the beaker with a piece of filter paper or something like that. Probably not parafilm, because it will eat through the parafilm, but you can use, some filter paper or something, and that will slow the loss of vapor and will promote rising. So the general process in a nutshell is we're going to prepare our capillary applicators, prepare mixtures and solvents, or our eluents if you prefer that term. We will dissolve the samples in the eluent, and then we'll make our slight pencil marks, set up our plates, spot the plates, develop the plates, mark the solvent front line immediately after we've finished developing, and then we allow the plate to dry before we do any visualization. This is an important step, because if you don't let the plate dry and let the solvent evaporate off of it, you can have some errant results when you view the plate. Something may not show up correctly, it might be hidden by residual solvent, or in some cases you will actually register some kind of a different movement It's just better that you let it dry instead of trying to, and it doesn't take long to do this. It probably takes at most maybe 2 to 5 minutes for most of the solvent to evaporate off of one of these plates. It's because they're pretty volatile solvents, and we usually do this in the hood. So that is important. And then also you need to have an appropriate technique for visualizing. And sometimes we do have to change up our techniques unexpectedly. So we'll talk about spotting. And these pictures are the best demonstration of spotting technique that I think are available still. These come from a book you don't use. This is Zubrick's book, and this was from the 6th edition, but he's had several editions since then. It's a little bit more expensive than the one you use, I think. But he shows you here how you make these capillary tubes correctly. And so it is important that you understand that. You heat the middle of the tube with the burner, then you remove the tube before you pull. You don't pull over the flame, you remove it. And only a couple seconds, because it does reharden fairly quickly. But you basically stretch from both ends after it's pulled out of the flame for about 1 second, and you elongate it here, and then you can break this spot. I think it's important for safety reasons that when you break this, you put a couple of paper towels and wear some gloves or something like that, and apply pressure gently that way and break it off in one shearing force motion, as opposed to trying to break it over the glass disposal or some other kind of method. We don't want you to get anything in your hand or, anything like that. So there is a correct way to break and a non-correct way. And I would prefer you use the correct way. So try to soften that. And as you can see, the goal here is to get this to be pretty thin. You don't want it to be very big. If it's large, you're going to deposit too much material. But another thing that's important is you don't want this to collapse in on itself and be closed off. It's got to be able to be open so you can actually absorb sample. And you use an open end. It's a capillary action-based movement. Then once you have your tube and you've got your sample loaded, you place it on the plate and you make a small spot in the place that you've set aside for that. And that's basically the spotting technique. That's really all there is to it. This demonstrates kind of how you would mark up the plate. So when you do that, 1 minute. All right. This is the pencil mark that you'll make. You don't want to go all the way across, just a simple tick mark on either side, just enough so that you can take a ruler later and measure distances with it. And really all it serves is just to line all your dots up so you can make sure you're putting all of your spots near the same area. You want it to be across this spotting line here that you're spotting your plate. You don't want them to be variant, because then your distances won't be true to each other. And so another thing you can do if you want to make sure that you're having enough space between your spotting and to kind of line up your capillary tube injector better, you want to make a little bitty tick mark here vertically so you can have some guides to kind of guide you in the process. And that's basically all you have to do to set up the spots. Now, once you've set up the spots, of course, you place it in the chamber and you let solvent travel up. And then when the solvent is done, you mark the solvent line or the solvent front that traveled. And there will be some example slides that show you what I mean. But once that's done and it's dried, we go to visualization. There are different kinds of visualization methods. There's destructive visualization, which is called destructive because even though we can see all the spots with it that have traveled, we will oxidize and destroy all the compounds in the process. So it's destructive. We can't recover any of that material. For this reason, we tend not to do that, and most of the time we use a non-destructive UV light method in order to visualize the plate. Now, the most basic of the destructive methods is the sulfuric acid and baking in the oven at 110 degrees Celsius for 15 to 20 minutes. There's another one that I put in the notes on this slide, which involves the use of a permanganate sulfuric acid solution in which the plate is soaked and then back of it is wiped off and sat on top of a hot plate and heated gently until it develops the visualization for you. And it does leave charred bits, so it's destructive as well. And the other methods that I mentioned on here as well are in and of themselves mostly destructive. It would be very hard to recover the material, but the reason that I put them here is because they are functional group dependent and can be useful. Do I expect you to remember all of them? No, because most of the reactions that are going on here you won't learn about until next semester. But what I would like you to be aware of is that there are different methods of visualization, and sometimes we need to choose a specific method for some things. At most, you could expect a matching question from that kind of information, but it's highly unlikely it would probably be quizzed on it at all. Mostly just for edification. As far as non-destructive goes, you've got long-wave UV and short-wave UV. Long-wave UV is the one we tend to use the most. It makes the background of the plate appear fluorescent green, and then spots will glow either as a shadowy kind of gray color, or they will sometimes themselves take on a color such as blue or red or some other color from which they emit due to the energy supplied to them by the UV. The other method is the shortwave UV, which doesn't make the plate glow green at all in the background. It remains the same color it is, but you can see spots with it. And the spots usually in that case appear kind of a shadowy looking gray color. They are harder to see, and this method is not as favorable in most cases as the long wave. This is an example of what I mean. So when you do long wave, you get this nice kind of lime green color, and the spots will be kind of variant in how they're colored. Some are red, some are blue, some are kind of this gray color. With the other, it's more of a fainter gray than this even, and there's no color here. Uh-oh. Function. Okay. And then there's a semi-destructive visualization, which is where you use iodine to develop it. It's semi-destructive because iodine will react with some substances, and then that makes them altered and you can't recover them in the same way. But a lot of times you can separate it from them because it doesn't always react with them. There are cases where you may not see something on a plate, especially if it's the first time you've run it. You should probably also do iodine to make sure that all of the compounds have been accounted for in the process. The process is almost the same as when you developed it in the beginning, except you use no solvent. You place the plate in the chamber, add 2 to 3 crystals of iodine, and pop the lid over it. The iodine sublimates, and the vapors penetrate the plate and go into the surrounding products that have traveled on the plate and give them a color, and it turns them kind of the same color as iodine. Essentially, they'll look a bit like this, because iodine has kind of a dark purplish brown looking color, and they tend to look kind of a dark brown color, tan maybe. It just depends on it kind of looks like that color, and so it'll make them show up like that. And sometimes you'll get a surprise because it will make something show up as a spot that you didn't realize was there because it didn't show up on the UV for some reason. Measuring a TLC plate is relatively easy. and we measure the plate in order to calculate retention factor of our various compounds. This is a method that we use in order to determine the resolution of a separation, and it is effective and works fairly well for TLC. It doesn't always work well for other chromatography methods, however. When we talk about other chromatography methods, instead of a retention factor, we often use what's called the retention time. But we won't get into calculating that until later on down the road when we talk about gas chromatography. And even then, it will be more of an observation than a calculation. There are two methods that you can use. The easiest method is if you take a ruler and you measure from the bottom of the plate using the side that you placed into the jar, which had the spot line closest to it, measuring from there up to the midpoint of the compounds that traveled along the plate and recording that distance, and then measuring from the bottom of that plate up to the top where you drew the line for the solvent front. So that gives you the two measurements that you use in the calculation. Now, that doesn't mean that that's the only way. There is an alternative way, and that would be that you can measure from the mark that you made at the spotting line up to the midpoint of the product that moved through the plate, and then measure from that same line to the solvent front line again. So it really doesn't matter what part of the plate that you measure from, so long as that you measure it consistently and match that distance to the solvent front. And in terms of the calculation itself, it's merely a fraction or a ratio. And as we said, it's a resolution measure predominantly for the separation. Now, here, when I've written it out, I've chosen to use the variable z. The reason that I use the variable z is because when you develop a plate, you tend to do this in the upright position. And by convention, we usually define the z-axis of a three-dimensional grid as being the axis that moves straight up and down within the plane of the page. And then we usually have an x-axis that kind of comes out of the page and a y-axis that also moves along the page, such that z and y are in this 90-degree orientation together. The difference being that when you actually measure the plate, you will measure in the x direction typically, since most people want to measure on a flat surface. This, however, does not affect the measurement. All it is here to do is demonstrate convention and demonstrate that it's the distance that we're measuring on the plate. It's also important that you remember that retention factor is a unitless calculation. So when you're doing this on a quiz or exam, it's important that you use the correct number of significant figures when you report your answer. For most of you, you will not be able to measure the retention factor with any greater significance than that of about 2 significant figures, because most rulers have centimeter markings, but those markings are only resolved to about 1 millimeter each. So you really can't get more than 1/10 of a centimeter in resolution from any of these methods. And you'll never have a plate that goes over like, 70 millimeters or anything like that. So that's predominantly what to keep in mind with these measurements, is just make sure that you're being reasonable about the level of precision and accuracy that you can have, and be sure that you're calculating it correctly. This is just an example that shows you kind of what I'm talking about. So This black line here and this black line here represent the starting line from where I would measure. So you can either begin at the very bottom of the plate and measure up to the midpoint of the spot for the particular compound, and then measure from that same point up to the solvent front line, or you can start from the solvent, well, where the solvent began, which would be at the spotting line right here, measure up to the midpoint of the compounds, record that distance, measure up from here on this line to the solvent front line, and then take it as the ratio that it's meant to be. What's important to remember about retention factors is that they are specific to specific compounds, but only if the conditions that are used for the TLC experiment are repeated exactly as they were when it was done. For this reason, we tend not to publish as much the retention times and retention factors of different compounds in these scenarios because it's difficult to ensure complete replication of the exact experiments. And because those numbers are so dependent on having those parameters matched equally, it tends not to be as useful a measurement for research purposes other than amidst the lab itself. So it is common for labs to circulate their own retention factor data because they tend to use the same protocols every time for different solvents and different workups of different compounds. This concludes the presentation. On Monday, we'll do a short TLC experiment, which will encompass some of these skills and terms, and hopefully by then you will have watched this pre-lab webinar and gotten a very broad view and a good demonstration of how you'll go about different aspects of that experiment. If you have any questions, please bring them to the didactic session where we can address them with everyone there. And I look forward to seeing you next week.